Hello students, welcome to today's class. In today's lecture, we will learn about system of particles and rotational motion. NCERT section 6.7 to 6.7.2. This is disclaimer. Learning objective. By the end of this lecture, you will able to understand the concept of torque, angular momentum, relationship between torque and angular momentum. So in today's lecture, we will cover first 6.7.1 moment of force or torque. Then 6.7.2 angular momentum of a particle. So in this lecture, firstly we will discuss moment of force, then angular momentum. After that, the relation between moment of force and angular momentum. So first is torque. Now here question arises, what is torque, or we can say what is moment of force. So when we try to open a door, tighten a bolt or use a wrench, we don't just apply force, we try to rotate an object. And this ability of force to produce rotation or turning effect about an axis is called moment of force or torque. If we talk about the definition, so we can say torque is defined as the measure of the force that can cause an object to rotate about an axis. So suppose here we have an object, and here two forces are present, F1 and F2. So F1 act hinges of this object, or we can say at the corners. So in opposite direction, F1 acts in upward direction and F2 acts in downward direction. So there is a turning effect because the forces act in oppositely. So the turning effect produced by the force is known as torque from the axis of this object or body. So torque is also referred to as a moment of force. Moment of force is equal to turning effect of force. Or we can say torque is a rotational analog of force because here it produces due to opposite forces at the corners of the objects. So one more example, opening a door. So applying force at the handle, far from hinge, high torque, and door turns easily. So applying same force close to the hinge, and in this case the distance is small, so the torque will be also small and it will be harder to turn. And this turning effect in real life, we change the distance to increase torque. So let's understand the torque by using an example. So consider a force F that is acting on a particle P. So we have a 3-dimension space, x-axis, y-axis and z-axis. So we have a particle in xy yz plane and that is point P, or we can say particle P, whose position vector from origin is r. This one, r is the position vector. So if we define it mathematically, so the moment of force, or we can say torque, that is denoted by tau. So this symbol is tau. So tau acting on the particle with respect to origin O, given by the vector product. So mathematically, the tau, or we can say torque, we can define r cross f. Here the important point to understand is r is the position vector from the origin and f is the applied force on the particle. Clear? Or torque is a vector quantity. It means it has both magnitude and direction. Let's see the magnitude and direction of the torque. So magnitude of moment of force, or we can say magnitude of torque, is tau equal to rf sine theta. So look at figure 6.18. We know tau equal to r cross f, cross product of position vector and force. So here tau is the perpendicular to the plane containing r, that is position vector, and force, and that its direction is we can determine using the right hand thumb rule, or we can say right hand screw rule. So f is the magnitude and r is the magnitude of the position vector respectively, and theta is the angle between r and f as shown in the figure. So look at figure, r is the position vector and f is the applied. So the angle between r and f is theta. All right. So if we draw a dotted line f in backward, so here r sine theta, this is the component of r. So if we draw the components of f, components of r, it will be r sine theta and r cos theta. And if we draw the components of f, so again there are two components. So we can say r sine theta is the perpendicular. R perpendicular is r sine theta. So we can write magnitude of moment of force r sine theta into f. Listen carefully, r sine theta is the magnitude form into f. So here r perpendicular f. F is the force. The important point here is this, r is not perpendicular. The perpendicular is the r sine theta, the components of the r, not r. So we can write tau equal to r into f sine theta is equal to r perpendicular, r into f perpendicular. So r perpendicular is r sine theta is the perpendicular distance from the line of action of the force f from the origin. So this one, line of action is this one, r sine theta, and the applied force. So the turning effect here known as torque. So line of action is imaginary line along the direction in which force is applied. So if here force is applied with angle theta, so we can say the imaginary line have along the direction in which force is applied. So F perpendicular is equal to F sin theta is the component of F in the direction of perpendicular to F. So when we resolve F, so there is a two components, F sin theta and F cos theta. So we consider only F sin theta because F cos theta is horizontal. So the effective component is F sin theta, and that is that is the component of F in the direction perpendicular to R. So we can say a moment of force vanishes if either the magnitude of force is 0 or if the line of action of the forces passes through an origin. So in that case, the moment of force is 0. Clear? Now, here the most important term, that is line of action of a force. So the line of action of a force is the imaginary straight line along which the force is applied, or we can say acts on a body. So line of action extends in both directions beyond the point of action of the force. Clear? Now again here a question arises, why is line of action is important? So it helps us understand the torque or turning effect. Torque depends on the perpendicular distance between the axis of rotation and the line of action of force, not just the point where the force is applied. So even if we applied force at the same magnitude but change its line of action, the torque will change. Alright. Magnitude and direction of torque. So now this is important concept to find out the direction of torque. So we know tau equal to R cross F, cross product of R into force. So if we want to calculate the force, if we want to calculate the direction of torque or find the direction of torque, so it is perpendicular to plane formed by R and F. So R and F both having in a plane, and the perpendicular, this perpendicular component is the direction of the torque. So we can determine the direction of the torque by using the right hand thumb rule. So right hand thumb rule says point of fingers, listen carefully, point of fingers of right hand in the direction of position vector R and curl them towards the direction of applied force F. So thumb gives us the direction of force. So here curl your fingers in the direction towards the direction of applied force. So the direction of applied force is this one and the R position is this one. So when we curl the R to F, the our finger is gives the our thumb is gives the direction of torque, that is perpendicular to the plane formed by R and F. All right. So tau is the direction of tau we can determine easily using the right hand thumb rule by curling the fingers towards the acting force. The SI unit of torque is Newton meter. So we can simply calculate this. So tau equal to R cross F. R is position vector, so unit is meter, and F is the force, a unit is Newton. So the combination R cross F is Newton meter. And dimensions of torque are same as the work and energy, that is ml square t raised to the power minus 2. How we can say? Because we know work done is equal to force into displacement. Yes or no? Listen, work done is equal to force into displacement. Force we can measure in Newton, and the displacement we measure in meter. All right. Similarly, here the formula of the torque R cross F. So the position R is the position we measured in meter, and F is the force we measured in Newton. So it will be Newton meter, and due to the same unit, the dimension formula is same as those of work or energy, that is ml square t raised to the power minus 2. All right. Angular momentum of a particle. Now uh, we will learn angular momentum. So here question arises, what is angular momentum? Yes or no? So just like a moving particle has linear momentum, p is equal to mass into velocity. So angular momentum is the rotational analog of linear momentum. It tells us how much rotational motion a particle has about a point of axis. If we talk about the definition, so the angular momentum L of a particle about a point is defined as the cross product of particles position vector R relative to that point and its linear momentum P. So we can say L is equal to R cross P. Mathematically, angular momentum L of a particle with linear momentum P at position R relative to origin O is defined as L is equal to R cross P. So R is the position vector or P is the linear momentum. Angular momentum is the rotational analog of linear momentum. Alright. Linear momentum P is equal to mass into velocity. Therefore, we can write L is equal to m into R cross P. Here P is the R cross V. Here we know P is mass into velocity. So mass is a constant term. So it comes outside. The remaining term is R cross V. So V is the velocity of the particle. Magnitude of angular momentum. So the formula is L is equal to R cross P given as L is equal to RP sine theta. So where R cross P is equal to RP sine theta by using cross product. This is the simple term, and P is the R and P is the magnitude of the position vector and linear momentum respectively, and theta is the angle between R cross P, R and P. R perpendicular is the perpendicular distance of the particle from the origin, and P perpendicular is the component of P in the direction of perpendicular to R. So angular momentum L is 0 when linear momentum of particles is 0. So in that case L equal to 0. So from this formula it is clear that L is depend on P. Yes or no? So particle is at the origin R equal to 0. In that case the angle between R and P is 0 or 180 degree. So angular momentum is what? 0. All right. So now uh, direction, direction of angular momentum. So similarly, as we find in case of find it in case the torque r cross f, similarly here we will find. So direction of angular momentum is perpendicular to plane of r and p. So we can determine it using the right hand rule. So look at here. R is the position vector. Yes or no? So point fingers from R to V. R to V in the direction of rotation and curl them. So thumb gives the direction of L. This one. Thumb gives the direction of L. And it is perpendicular to the plane formed by the position vector and velocity vector. And its SI unit is kilogram meter square per second or joule per second, joule second. Dimension formula is ml square T inverse. Now we will discuss relationship between torque and angular momentum. So we know angular momentum of particle, that is L is equal to R cross P. Now the next steps is very simple, because in this section we will discuss only mathematical terms, because this is the relationship between torque and angular momentum. So L is equal to R cross P. So differentiating with respect to time t, this formula it will be dl upon dt is equal to r cross p upon dt. So we will differentiate it with respect to time. So using product rule for differentiation, it will be dl upon dt is equal to uh, dr upon dt cross p plus r cross dp upon dt. Now we know rate of change of position vector of the particle, that gives its velocity, that is dr upon dt is equal to v. From the first lecture we know, from the second lecture we know dr upon dt is v. Rate of change of position gives us velocity. So linear momentum of the particle is mass into velocity. So dr upon dt into p, it will be equal to what? It will be dr upon dt is v, and v is mass into velocity. Here the vector product of two parallel vectors vanishes. So relationship between torque and angular momentum. So therefore we can write dl upon dt is equal to dr upon dt cross p plus r cross dp upon dt. So dl upon dt is equal to r cross dp upon dt. So from Newton's second law, the net force on the particle, that is dp upon dt, rate of change of momentum. So thus the time rate of change of angular momentum is r cross f. Dl upon dt is equal to r cross f. So and dl upon dt is what? Tau, because we know tau equal to r cross f. So where r cross f is the torque, tau acting on the particle, so we can say that time rate of change of angular momentum of particle is equal to torque acting on it. Therefore we get the rotation analog of Newton's second law. Now we will summarize it. First, torque is a measure of rotational force defined as the cross product of position vector and force. So r is equal to tau equal to r cross f. The magnitude of torque can be expressed as a tau equal to r cross f sine theta. So tau equal to r perpendicular f. Here r perpendicular is r sine theta. Clear? R perpendicular is to perpendicular the distance from the axis of rotation. And angular momentum of the particle is defined as the cross product of position vector and linear momentum. So mathematically it will be r cross p is equal to L. So magnitude of angular momentum of the magnitude of the angular momentum is given by L is equal to rp sine theta and L equal to r perpendicular p, where r perpendicular is the perpendicular distance from the axis. And time rate of change of angular momentum is equal to torque acting of the particle. So dl upon dt is equal to tau. Now we have some questions and this is homework for you. First, calculate the torque if a force of 5 Newton is applied perpendicular to a lever arm of 2 meter. Determine the perpendicular component of a 15 Newton force that makes an angle of 45 degree with a lever arm. Third, find the angular momentum of a 5 kg particle moving with velocity 2 meter per second at a distance of 3 meter, making an angle of 90 degree with its motion. If torque is 20 Newton meter and force applied is 4 Newton, calculate the perpendicular distance of the force from the axis. And why does angular momentum remains constant in the absence of external torque? So these are the practice questions and this is homework for you. All right. Thank you for your attention.